Next, we're going to learn how to solve and graph logarithmic functions and apply their properties. But first we need to know just what is a logarithm. What is this thing we call a logarithm? Well, think back, this was probably last year or maybe earlier this year when you learned it, that when you want to find an inverse of a function, I'm going to start with a simpler example. Maybe our function looks like this. The first thing we do is replace f of x with y. Then we switch x and y and solve for y by adding 2 to both sides and dividing by 3. And then we replace y with f inverse of x. Hopefully that looks a little bit familiar to you. When we graph both of these functions, the function and its inverse, they're going to be reflected across the line y equals x. So you can see in our example here we have this blue curve. This is the line y equals 2 to the x. That's an exponential function, just like what we've been studying in step 19. If I reflect that over the line y equals x, I get its inverse, which is the red function here. That function is x to the by, and y is considered the logarithm of x in this example. Y equals log base b of x is the notation that we're going to use, and we read it y equals log base b. This little number here, this subscript, is the base of x. One thing to note, if the log base 3 of 27 equals y, then 3 to the y power equals 27. We're going to use that in a couple of examples. The first thing we want to do, though, is be able to translate between logarithmic notation and exponential form. That's very important to be able to do those things. And I like to use almost what looks like a cursive letter E. I want to start with the base and put in an exponential form, E for exponential. If you can remember that E, that will help you rewrite this. We're going to start with 2, then we go over to 3, that's our exponent, because remember a logarithm is an exponent. Then as we come back around this curve, we're passing over the equal sign, 8. Do you agree? Is 2 to the third power 8? It sure is. Let's try this next one. 4 to the negative 4. 4 raised to the negative 4 power equals 1 over 256. Let's see if that's right. 4 raised to the negative 4 power equals, and now I'm going to press math, enter, enter to bring it back as a fraction, 1 over 256. Pause the video and try these next two. Hopefully you got 4 squared equals 16. 3 to the 6th equals 729. Let's go backwards now. We're going to start with things that are in exponential form, and we're going to change them to logarithmic form. When we change them to logarithmic form, we start with the word log. Now, when we studied step 19, we know that this was the base. This 15 is the base. And 3 was its exponent. So when we write the base, it's going to be this small number, kind of the subscript, if you will. I remember it because the base of a pyramid or the base of anything is usually low to the ground. It's not high up in the air. So the base stays low. We put the base low. The log base 15. Now, we only have 2 numbers left, 3 and 3375. If I start by putting a 3 here, it's going to look just like I'm copying this equation, and I don't want to do that. So I'm not going to use the 3. I'm going to use 3375 equals the number that I have left, 3. Another way to think about it is to try to make that e again. We're going from exponential form. The log base 15 of 3375 equals 3. The order matters, and that can be the most challenging part of these types of problems. The log, our base, is the bottom number that has the exponent of 4. Our log base 4 of 2, equals 1/2. Pause the video and try these next two. Now, this can be very helpful when we're trying to evaluate a logarithm. We haven't learned the change of base formula just yet. We will do that later on in this step. But for now, we know that this is just a number. The log base 16 of 4 is some number, but we don't know what it is. So we call it x. It's in logarithmic form, so I'm going to convert it to exponential form. I'm going to say 16 to the x equals 4. And now, it's just like I'm back in step 19, finding a common base. I'm going to express 16 as 4 squared. Now I have the same base, 4 to the 2x equals 4 to the first. 2x equals 1. So, x is 1/2. So now I know that the log base 16 of 4 is 1/2. Let's try another one. We don't know what this equals, but it equals something, so we'll call it x. 3 to the x equals 81. Now I'm going to express 81 as a power of 3. So 3 to the x, I'm going to call it 3 to the 4th. They have the same base, which means their exponents must be equal as well. Last one, 1/2 to the x equals 256. Now, I need to change both of these bases. We haven't done a lot of this, but I'm going to change 1/2 into 2 to the negative 1, because that's the same thing. 2 to the negative 1 is 1/2. And on the right side, let's use our calculator to verify since I don't have my chart handy. 2 to the 9th. It's too big. 2 to the 8th is perfect. So 256 is 2 to the 8th. Multiplying my exponents, now I have a common base. Negative x equals 8. So x equals negative 8. Let's talk about the graphs of logarithm. A logarithmic function can be graphed just like we graphed exponential functions. They're going to look very similar. The domain of the parent function log base b of x is always going to be from 0 to infinity. We have an asymptote here at the y-axis. The range is from negative infinity to positive infinity for both functions, whether the base is greater than 1 or the base is a fraction. Remember, when we talked about exponential functions, our base could be greater than 1. That indicated exponential growth. Or our base could also be a fraction, which was exponential decay, but our base could never be negative. And the same is still true. The base of our logarithm cannot be negative. We're going to take advantage of technology to help us graph these logarithmic functions. For the first one, I'm going to go into y equals and clear out anything that's there. Now not to get ahead of ourselves with the change of base formula, but we're going to need to use that to get this to type into our calculator. We want to type the log of x divided by the log of 5. That's the only notation we can use to get the calculator to use a base of 5. So we're going to type the log, which is next to the 7, of x divided by the log of 5, close parentheses. Then I'll graph it. We see what the graph looks like, and we need a table of values, so second graph, and we can see that if I try to scroll up, I'll just get error. So our graph is going to start at 1, 0. That's the first nice point I see, which is right here. And the next nice point I see is 5, 1. And then I can look at my chart here to see what kind of points. What are we approaching? We're getting higher very gradually. As far as the graph goes, it's never going to get higher than 2 on my graph. So I'm going to connect these points as nicely as I can, draw an arrow, and again it approaches this asymptote of the y-axis. So now I've graphed my first function. Let's try the next one. Instead of using our TI calculator, I'm going to use Desmos to show you how you can type it with Desmos as well. When you pull up your Desmos calculator, you open the computer, the little keyboard at the bottom, and press Functions. We want to go all the way over to Miscellaneous. We'll press Log. I forget what the problem is now. Log base 1/3 of x. So log x goes on the top, divided by, I'll go into my functions again and press log 1/3. And again, I can press this gear shift right up here at the top to access the table. 1, 0 is a nice point. 3, -1 is a nice point. That's probably all the nice points I'm going to get. 1, 0, 3, -1. 1, 0, 3, -1. It is still an asymptote with the y-axis. This way. It gives us a nice sketch of the picture. Just like all of our other functions that we've studied this year, we're going to be able to do transformations of logarithmic functions. H is still going to control the left and right movement. We're going to go right if we add a number with x, and we're going to go left if we subtract a number from, I think I said that in reverse. If we add a number, we're going to go left. If we subtract a number, we're going to go to the right. Vertically, if we add a number, we're going to go up. If we subtract a number, we will go down. This coefficient out front, the a value, if it's negative, it makes the graph reflect across the x-axis, just like it's always done. If it's greater than 1, we're going to have a vertical stretch. If there's a fraction before the logarithm, we're going to have a vertical compression. So let's take a look. We're comparing this function, this logarithmic function, to its parent function, which would be log base 10 of x. What is different between these functions? Well, I'm going to highlight what's the same. So that means I need to explain what the 3 does and explain what adding 1 does. 3 is an a value and it's greater than 1. So there's going to be a vertical stretch. adding 1 outside the function is a k value, and it's positive, which means it's going to go up. There's also a vertical shift up 1. Let's look at the next one. Again, our parent function is the log base 1/4 of x. The log base 1/4 of x, so that's the parent function part. What's changed? Well, we have a coefficient of 1/2 before the log, and we also have subtract 3. That's what's making it different from the parent function. And we're subtracting 3 within the parentheses with x. So the 1/2 is going to cause a vertical compression, and subtracting 3 is causing us to move right 3 units. These do not have the parent function listed, but we can go ahead and write the parent function above it. F of x, we start with the log base 3 of x. The parent function right here would be the log base 1/2 of x. So let's compare. How have they changed? Go ahead and pause the video and try these last two. There were 2 transformations in our first example on the left, a vertical stretch and a shift right 2 units. In our second example, there were 3 transformations. We have a vertical compression because of the factor of 1/4. We move left 1 unit because we added to x within the parentheses, and we've gone down 5 units. So it would move the parent function in those directions.